Okay, hello everyone. In this video, we are going to discuss about Gauss law and its applications. Okay, so let's start. Now, according to the statement of Gauss law, it states that for any distribution of charges, the total electric flux, that is your phi subscript of E linked with a closed surface, is equal to 1 by epsilon times of the total charge, that is your q total enclosed by that surface, mathematically represented by phi e equal to q total by epsilon 0, or this phi e can be represented as surface integration of E dot ds equal to q total by epsilon 0. Here E is represents the electric field intensity. Okay, and here electric flux is nothing but the electric lines of forces passed through that area. If we are going to say that electric flux through an area, suppose this is your area and electric flux through this area means numbers of how many numbers of electric lines of forces, these are electric lines of forces. Okay, numbers of electric lines of forces passed through this area, this is nothing but your the so called your electric flux. Okay, and here in the statement it has been written that a closed surface, always we have to remember this closed surface should be a 3D one, a 3D closed surface. So always we have to imagine or remember that here the closed surface means a 3D closed surface. Okay, so here we can see that a plus q charge is enclosed by a 3D cube, 3D cube or rectangular box. So total electric flux will be passed through 6 phases, this one phase, at the bottom one phase, this side, this, so 6 phases. Through 6 phases, how many numbers of electric flux is going to be passed through by this closed surface or 3D closed surface is nothing but equal to q total by epsilon 0. Here q total means the total charge enclosed by this 3D surface. Okay, so again I am going to read this statement. Electric flux linked with a closed surface means, here closed surface means a 3D, always we have to imagine 3D closed surface equal to total number of charge enclosed by this 3D surface by epsilon 0. We are going to take one example. Suppose inside this cube another minus q charge is going to be present. So here plus q minus q, if I am going to add, then it will be 0. So net electric flux through this 3D surface will be equal to 0. That means phi e for this case will be equal to 0. Now consider another example, simple example, that how much flux we are going to expect for a particular surface. Actually this rectangular box has 6 faces. Okay, so for each face, this one face, this one face, so for each face, each one of the face, what will be the flux? So here if we are going to consider q plus q charge enclosed by this 3D surface, so total flux for this case will be equal to capital Q by epsilon 0. That means for 6 phases, this much flux, that is your Q by epsilon 0. So for one phase, for 6 phases, okay, for one phase it will be 1 by 6 Q by epsilon 0. Okay, so if in your exam it will ask the question that any one of the phase, through any one of the phase, how much flux is going to be passed through if q amount of charge is enclosed then the answer will be 1 by 6 into q by epsilon 0, this one. Okay. Okay. Next we are going to go for the applications of Gauss law. So consider our first application of Gauss law is to calculate electric field intensity at any point from non-conducting charged flat sheet. So this is a non-conducting, or we can say dielectric charged flat sheet, which is uniformly charged, and having sigma is the surface charge density, that means charge per unit area. If we are going to consider a unit area here or here or here, so in this unit area we can found the charge how much, sigma. This is the uh, non-conducting charge sheet which is given. And here you can see, if it is charged by positive charge, then electric lines of forces will be like this, along outward. So this side will be along this side, this way. Okay. So if we are going to find out the electric field intensity at any point from this charge sheet, suppose at point P or Q, by using Gauss law, we have to consider a 3D Gaussian surface. So here we consider a 3D Gaussian surface is a cylindrical surface, is this one. Okay. We consider a 3D Gaussian cylindrical surface, and the total Gaussian cylindrical surface is divided into three surfaces. So here at point P, the flat surfaces is named as S1. At Q, this flat surface is named as S2, and the entire curved surface is named as S3. That means the entire Gaussian cylindrical surface is divided into three surfaces. Okay. According to Gauss law, total electric flux passed through 3D surfaces. So 3D surface, that means 3D Gaussian surface, mathematically E dot ds will be equal to charge enclosed by epsilon 0. That means total electric flux passed through this cylindrical surface, or if we are going to find out the electric flux passed through S1, S2 and S3, and then we are going to add the electric flux passed through S1 and S2 and S3, then we can find this one, charge enclosed by the Gaussian cylindrical surface by epsilon 0. We are going to do so now. For that, we consider a elementary area at any point on the Gaussian surface or your Gaussian cylindrical surface. First, we are going to consider a small area ds on this S3, on the curved surface, this one named as ds3. So here, if we are going to consider this is your ds3, so obviously direction of ds3 will be this one, and we know that the electric lines of force coming from this charge sheet is outward, like this, is outward. Okay. That means along x axis, but ds3 direction is your along y axis. Okay. So if we are going to consider the E dot ds3 will be 0, because E vector and ds3 will be perpendicular with each other, so dot product will be 0. So E dot ds3, so here if we are going to consider for this surface, electric field intensity direction is along this direction, ds3 is your along this direction, so angle between them is 90 degree. So E dot ds3 will be 0 at all the points on the curved surface. So if we are going to consider ds3, and the flux through the ds3 will be 0. If we are going to consider here on the curved surface, then ds3 direction will be like this, and electric field intensity will be along this direction, angle between them 90 degrees. So flux through this ds3 on the curved surface will be equal to 0. So from the figure we can found E dot ds3 will be 0 at all the points on curved surface S3 except all points on S1 and S2. So S1 is the surface is this one at point P, this flat surface is your S1 and this flat surface is your S2. So at point P we have to find out total flux passing through the surface S1. First we are going to consider a ds1, a small ds1 on the surface S1. So if this is your ds1, so obviously direction of ds1 will be along this direction here, and e1 direction is along this same along positive x-axis direction. So both have the same direction. So angle between them will be 0, cos 0. So dot product of these two vectors will be E dot ds1 into cos 0 degree will be equal to cos 0 degree equal to 1, and E is your constant taken outside. ds1 integration if we are going to consider, then we can found E into S1. Okay, so that means ds1 integration means this total surface area, flat surface area, that is your S1. So we found total flux passing through this surface S1 is your ES1. Similarly, we can found total flux passing through this surface S2 will be ES2. How it is? Here you can see, if we are going to consider a small elementary area ds2, then ds2 direction along this direction and E2 direction also along this direction. So angle between them is 0. So we can found the total flux passing through this S2 surface area which is at Q will be ES2. Okay. Now total electric flux passing through the 3D Gaussian surface, 3D Gaussian cylindrical surface, that is your E dot ds. Here closed, you have to put a closed circle which is represent the surface integration. Okay, E dot ds, this one E dot ds will be equal to how much? ES1 plus ES2. For S3, at all the points on the S3 flux will be 0, so that value will be 0. That means for S3 it will be 0, but as for S1 and S2, the electric flux passing through S1 is your ES1 and S2 is your ES2. S3 is your 0 plus 0 equal to how much? Equal to 2ES. Why it is 2ES? From the figure you can see, we consider that this surface area, this surface is your S. Okay, this surface is your S. So this surface value or magnitude is nothing but S1 and S2. So from the figure S1 and S2, this one is your S2. Wait, I am going to correct it. So S1 and S2, S1 and S2 equal to S. Okay. So now we are going to calculate total charge which is enclosed by 3D Gaussian cylindrical surface. So here you can see, by this 3D Gaussian surface, the total charge enclosed is nothing but contained by this surface. So charge contained by this surface is nothing but charge enclosed by this 3D Gaussian surface. So surface area of this surface is your S. Per unit surface area, how much charge is given? That is your sigma. So on this S surface, how much charge will be? That is your sigma into S. Okay. So on this surface area, the total charge present, that is your sigma S, which is enclosed by this Gaussian surface. So according to Gauss law, total electric flux passing through the 3D surface, here total electric flux passing through 3D Gaussian surface, that is your 2Es will be equal to how much? That is your Q enclosed by epsilon 0. Here Q enclosed by the Gaussian surface is how much? Sigma into S. So as per the Gauss law, this value, total flux, that is your 2Es equal to sigma S by epsilon 0. So that implies we found electric field intensity at any point, that may be at P or Q, will be equal to sigma by 2 epsilon 0. Okay. Now we are going to go for the next application of Gauss law, that is your electric field at any point in between two parallel and opposite charge sheets, that is your parallel plate capacitor situation. This one for 2A situation, that means point is considered in between the two plates, two parallel plate capacitor, and 2A, for 2A point is situated at the outside of the parallel plate capacitor. So what will the value if the point will be inside the parallel plate, outside the parallel plate, what will the value? Okay, so here you can see for any charged sheet, we found at any point either P or Q, the electric field intensity value is your sigma by 2 epsilon 0, right? So here in this case there is two sheets, which is this sheet is charged by a positive charge, this one is your negative charge. So if we are going to put a unit positive charge over here, the electric field intensity direction due to this sheet will be along this direction, that means repulsion by this sheet, attraction by this sheet, this one. So here E1 represents E1 electric field intensity due to positively charged sheet, and E2 is your electric field intensity due to negatively charged sheet. And just we found that for a particular one sheet, electric field intensity at any point is your sigma by 2 epsilon 0 is the magnitude. So for this sheet, what will the magnitude? The magnitude will be sigma by 2 epsilon 0. For this sheet, what will the magnitude? Sigma by 2 epsilon 0. And we found from the figure both E1 and E2 are the same direction, so their vectorial is going to add up. So net electric field intensity at point P, when the point P inside the parallel plate capacitor, will be this value plus this value. The magnitude we are going to consider, this is your sigma by 2 epsilon 0, sigma by 2 epsilon 0, this is your sigma by epsilon 0, which is most important expression that you have to remember, which will be useful for your to understand the dielectric behavior inside a parallel plate capacitor. Okay, so inside the parallel plate capacitor at any point, electric field intensity will be sigma by epsilon 0. Okay, now we are going to consider if the point lie outside of the two parallel plate capacitor, that means point P is situated over here. So as we discussed that E1 is due to positive, E1 is the electric field intensity due to positively charged sheet. So if we are going to put a positive unit positive charge over here at point P, then due to this sheet it will be repelled along this direction, that means U1 direction will be along this direction, negative x-axis direction, and this unit positive charge will be attracted by this sheet. So due to this negative sheet, the electric field intensity E2 will be along this direction, both are opposite with each other, E1 and E2. And as we know that electric field intensity due to a single sheet is your magnitude of a single charge sheet is your sigma by 2 epsilon 0. So due to positive charge, this is your sigma by 2 epsilon 0, negative charge sheet sigma by 2 epsilon 0, but both are opposite with each other. If I am going to add, then vectorially they are going to cancel with each other, that means this value will be subtracted this value. So these two values are going to be subtracted with each other because both are opposite with each other. So hence we found at point P, which is outside of the parallel plate capacitor, magnitude of electric field intensity will be equal to 0. Okay. So our next application of Gauss law is your electric field intensity at any point due to a linear charge distribution. For that we consider a infinite long wire which is charged by positive charges. That means positive charge is uniformly distributed on this infinite long wire. So here consider a infinite long charged wire which is uniformly charged, okay, and its linear charge density, that is your lambda. So here linear charge density means a unit length, per unit length. Suppose if we are going to consider this is your unit length, the charge is your lambda. If I am going to consider here is unit length, then charge on the unit length will be lambda. So charge per unit length is given as lambda. Now to find out the electric field intensity at any point from this linear charge distribution, suppose at point here, here or here, suppose P or Q, for that if we are going to consider the Gauss law, we have to consider a Gaussian surface. So this is a Gaussian surface, imaginary Gaussian surface which is looks like cylinder, okay. So to find out electric field intensity at point here, we have to consider a Gaussian surface. So here the Gaussian surface is a cylindrical one, okay. Now here the same thing it has been written, consider 3D Gaussian cylindrical surface as shown in the figure. Let length of the Gaussian surface is your L, length of this Gaussian surface is your L. Hence the total charge enclosed by 3D Gaussian surface, here you can see the length is how much, is your this one, is your L. Per unit length charge is lambda. So in this length L, what is the charge enclosed by this Gaussian surface, will be lambda into L, okay. So according to Gauss law, we know that electric flux or total electric flux passing through this Gaussian surface will be nothing but charge enclosed by epsilon 0. So here total charge enclosed by this Gaussian surface is your lambda L by epsilon 0, right. Now we are going to consider three surfaces. Here this one is one flat surface S1, this one at the bottom another flat surface S2, and the curved surface we consider as S3. Here I can see that if we are going to consider a small elementary surface on S1, then the direction of ds1, suppose this is your ds1, the direction of ds1 is along positive y-axis direction, but however the electric field intensity direction is along this direction. So angle between them is 90 degree. So the electric flux passing through this S1 uh, surface area will be always 0, because wherever I am going to consider here or here or here through this elementary surface, the electric flux will be 0. Or we can say, if we are going to consider entire surface S1, this surface direction is along positive y-axis direction, where electric field intensity which is coming out from this linear charge distribution along this direction. So both are 90 degree. So if we are going to consider E dot ds1 dot product, the cos 90 will be 0. Likewise, if we are going to consider S2, here S2 on the S2, if we are going to consider a small surface ds2, then ds2 direction will be along this direction, where the electric field intensity is along this direction. So the angle between the electric field intensity and ds2 is your 90 degree. So E dot ds2 will be equal to 0. So hence electric flux passing through these two surfaces S1 and S2 will be 0. So here the same thing it has been written. Consider ds an elementary area at any point on the Gaussian cylindrical surface. From the figure, E dot ds1 and E dot ds2 will be equal to 0 at all points on S1 and S2, whatever we have been discussed, except all points on the curved surface. On the curved surface, suppose here on the curved surface, if we are going to consider one elementary area ds3, then ds3 direction is along this direction. So ds3 direction and E direction both are same, or both are along along one direction. So E dot ds3, that is your E ds3 cos 0 degree, cos 0 is your 1, E into integration of ds3. ds3 means integration of ds3, that means total surface area of this curved surface of the Gaussian cylindrical surface. So what will the surface area? Here this is the length L, and radius we considered as r. Radius of this cylindrical surface we consider r. So total surface area will be 2 pi r into L. So we found the total flux passing through this entire Gaussian cylindrical surface is your E into 2 pi r L. However, flux through S1 and S2 will be 0. So only if flux is passing through the S3. So total flux passing through entire this Gaussian cylindrical surface is your E into 2 pi RL. So according to Gauss law, this one E dot ds, here you have to write like this: a enclosed a circle which represents the surface integration. So E dot ds equal to E into 2 pi RL we found. As per Gauss law, this E into 2 pi RL will be equal to how much? Charged enclosed by epsilon 0, we found lambda L by epsilon 0. Finally, we found electric field intensity at any point from this linear charged distribution will be this one by 2 epsilon 0 into lambda by r. Some books has been written as like this: 1 by 4 epsilon 0 into 2 lambda by r. Same thing here, 2 multiplied and 2 divided. So you just remember this one. So I suggest that you have to remember the last expression, which are very much essential for your exam point of view. So for linear charge distribution, electric field intensity at any point will be this one. For parallel plate capacitor, if the point P inside, the sigma by epsilon 0, outside is your 0, and for a flat sheet charged by positive charge is your sigma by 2 epsilon 0. In our next class, we are going to discuss electric field at any point due to charged spherical shell. Okay, in detail we are going to discuss in our next class. Thank you so much for watching this video. Thank you.